Hello, Algebra 2. Tonight's topic is Unit 8, Day 1, Graphing Rational Functions. Our essential question for today is, how do I find the gaps in the graph of a rational function? Starting off, I just want to start off with the definition of what is a rational function. A rational function is a function that you can write in the form of f of x equals p of x divided by q of x, where both p and q of x are polynomials, and q of x cannot be equal to 0. So just like when we were doing rational expressions in our last unit, we have two items that are going to be divided. So we have something in the top being divided by something in our denominator here. And again, our denominator cannot equal 0, or it would be undefined. So let's take a look about how that looks. Today in class, you graph some of these functions when it came on Desmos.com, or some of you used a graphing calculator, and it was kind of interesting to look and see where the gaps were of these functions. And tonight's videos, you're going to learn the rules to help you uncover them, but you can always go back to tracing it out to find out where those gaps are. So the first thing is to realize what the parent rational function is. Just like all of our other functions, quadratic, absolute value, we have a parent function when it comes to our rational function. In our parent rational function, we have the same letters that we're used to seeing throughout, our A, H, and K, and it would be written in this way. Most of the ones you did in class were not in the parent function form to help you use. So we'll sometimes see it in this form, and other times we'll have to do it the way we did in class and graph it by hand using the rules and also having the calculator to check. So again, H moves it left and right, our K moves it up and down, and then A would stretch or reflect it horizontally. The way our parent function is, our A is 1, and our H and K is 0, and that function is 1 over x. So just like all of our parent functions, our A is always 1, and our H and K is 0. So anytime you don't know what a function looks like, we can always use our table to find out. Remember, we can input our x's and output our y's to see what the graph looks like. So go ahead and input some values into x and see what you can come up with the y. Go ahead and pause the video and try that. Okay, so here's some values that I chose. My first, if I input -2 in for x, I have 1 over -2, so that would make that -1/2. And then if I input -1 in for x, I have 1 over -1, which would be -1. And then if I tried to input 0 in for x, that's impossible. We can't divide by 0, so it's going to be undefined at 0. If I input 1 for x, I have 1 over 1. So this is what I'm doing in each step. 1 over our x, in this case it's 1 over 1, so that is 1. For when I input 2 for x, we have y equals 1 over 2, so that's 1/2. And then if I input 1/2 in for x, so y equals 1 divided by 1/2, remember what that would do. 1 divided by 1/2 would be 1 times 2 over 1, because we always, when we're dividing by a fraction, we multiply by the reciprocal, and we'll get 2. And so if we had 1 over -1/2, we would have 1 divided by -1/2, and then 1 times -2 over 1 which would result in -2. So go ahead and now try to plot these points if you haven't yet, and then bring it back. Okay, so you should, when you've plotted your points, you should see two sections similar to what we saw in class today. And then the gaps, you should see that there is a vertical asymptote of x equals 0 and of y equals 0. So the function is going to be approaching. And let's talk more about what an asymptote is. But first, before you move on, make sure your graph, you have the parent rational function graph correctly. Okay, so an asymptote is in a line that the function is approaching. So again, an asymptote is a line that the function is approaching. And if you take a look back at our, and just up for you, but back on my slide here, the vertical asymptote again is a vertical line, and the function is approaching it here and also here. For a vertical asymptote is when the function is undefined, so it cannot cross that vertical asymptote. A horizontal asymptote, the function is approaching it, and we've been talking about these with end behavior, and next year, either in your next year's math or in college, you'll be learning more about what that means. But our graph can touch a horizontal asymptote. Usually we draw it as it's approaching it. But our horizontal line here, the function is approaching it. Okay, so an asymptote is a line that the function is approaching. And how do we find our horizontal asymptotes? So remember, horizontal asymptotes, think of their horizon, like on the sea, what kind of a line it is. So they will be horizontal lines. There's three possibilities when we have a horizontal asymptote, and you can only have three possibilities. You can either have a possibility where the degree of the numerator is less than the degree of the denominator, or it could be greater than the degree of the denominator, or they could be equal. Now remember what a degree is, and this is a couple units back, but remember what a degree is. Our degree is the highest exponent that a function has. So when we're talking about our rational functions, we have a function in the numerator and in the denominator. So if we just would look at a first example, and this example was not one given to you in our today when we did not graph this type of example. But if we had x minus 1 divided by x minus 1 times x plus 2. So in this case, we have a degree where the numerator has a less of a degree than the denominator. Our degree in the numerator would be 1 because our highest exponent here is 1. And that's again the multiplied through part of our polynomial, because here our degree in our denominator, we would have to multiply it out to see what that is, and in this case it would be 2, because it would be x squared minus x plus 2x minus 2, so that would have a degree, the highest exponent there would be 2. So here our degree of the numerator would be 1 and our degree in the denominator is 2. So in this case, our numerator is less degree than our denominator. So when that happens, it will have a horizontal asymptote of y equals 0. You don't have to worry about anything else. Once you determine the degree, if it's bigger in the denominator, it's going to be y equals 0. Now, in the case of the opposite, we did have an example where you saw this. An example of that one, that was the one where the graph was y equals x minus 3 times x plus 4 divided by x minus 3. And remember that that turned out to be a line. Remember there was a gap in the graph at 3. Remember when you were graphing that in your discovery today. So the function turned out to be a line with a gap in it at the value of 3. And we're going to talk about what that means in a little bit. But for this purpose, for just understanding the horizontal asymptote, when this happens, when the degree is greater in the numerator than the denominator, because we would have a degree of 2 here, because we multiplied that out, it would be x squared, and the highest exponent would be 2, and then the denominator here would have a degree of 1, then we would not have an asymptote. And that should make sense to you, just like you saw it when you looked at this today. It was just a line. So that will not have a horizontal asymptote. The only other possibility is if the degrees are equal. So in that case, if the degrees are equal, it's going to have the ratio of the leading coefficients. So if you want to see how that looked, remember our last example that we did with the rational functions was the y equals 5x squared minus 17x plus minus 12 divided by x squared minus 16. Now this one, they have equal degrees, so degree of 2 and a degree of 2, so it's going to be the ratio of our leading coefficients. Remember what a leading coefficient is, it's that number in front of the highest degree. So our numerator is 5, the leading coefficient would be 5, and the ratio would be 5 over the leading coefficient in the denominator, which would be 1. So our horizontal asymptote would be y equals 5. Okay, for vertical asymptotes, remember this is where a function is set equal to, is where the function's undefined. So the way we find it is we set our denominator equal to 0 and solve for x. A hole is a point in the graph where the function is undefined. So if you take a look at our example from the previous settings, here, this x minus 3 and x minus 3, that would be a hole in the graph. It would not be a vertical asymptote. And a hole is a point in the graph where the function is undefined. The way we find holes is when you see that common factor, just like the example I just showed of x minus 3, you would set that common factor that's in the denominator and the numerator equal to 0 and solve for x. So in the case of the one we just saw, it'd be x minus 3 equals 0, so x is 3. Then we're going to plug that value back in to the simplified function to find a y value. Because a hole is a point, it's going to have be a hole in the graph at a particular point. Our last item is how do we find a 0 of a rational function, and that is going to be when we set the numerator equal to 0 and solve for x. So if you think about what a 0 is, remember that would be when y equals 0, and so if you were to set the function x minus 3 divided by x plus 4 equal to 0, and if you think about a fraction, for this whole fraction to be equal to 0, only that numerator would have to be equal to 0. So that's why we find it in that manner. Alright, let's take a look at our first example. And it is this x minus 3 divided by x plus 4. So we can use what we just learned to help us find the gaps. And the first thing is to set our 0 equal to 0, to find our zeros. We set our numerator equal to 0, and we've solved for x, and we found a 0 of 3, 0. For our whole, remember a whole is if it has the same factor in the numerator and the denominator, it doesn't. So in this case we do not have a whole, and it looks like we're going to need a second short video So I'm going to stop here and ask you to hit play on the next video just to make sure you understand these examples. So another